All right. So first, quick review of what we talked about on Tuesday. We were talking about how we can look at means in a very similar way that we were looking at single individual values. So if we have a variable of x of a population is normally distributed with the mean and standard deviation, then for a sample size of n, the variable is also normally distributed. The mean is the same, and the standard deviation is the original standard deviation divided by the square root of whatever my sample size is. So that's basically what we covered on Tuesday, those formulas that we used. All right, so let's look at a couple really quickly. What is if I'm doing a sample size, so we're looking at IQs. My normally distributed is, my mean is 100, and my standard deviation is 16. So if my sample size is 4, what's the mean? Correct. My mean is still 100. What's my standard deviation?
16 is the standard deviation.
Of my sample size of 4. Remember, the standard deviation does not stay the same. So this is my 16 divided by the square root of 4, which in this case is 8. So your mean stays the same, your standard deviation does not. Your standard deviation is that formula right there. Yes?
Are there going to be cases where the mean does change?
No, there's going to be cases where you don't know the mean. So, in which we're going to start looking at briefly today.
So that formula for the standard deviation explains why the standard deviation does not stay the same.
Yeah, because there's a formula for it. It changes. So you got to, we'll do 16 and I'll show you the charts of it. What's the mean for if my sample size is 16? Still 100. And what's my standard deviation in this case? It's 4. So it's 16 divided by the square root of 16, which is 4. So in essence, what we're doing and what we're looking at is this. I'll give everybody a chance to finish writing that down and then I'll show you. So if I just take a single person and I want to know where their mean would fall on that curve, my mean is 100 and my standard deviation is 16. And we can figure out the z-score and all that other stuff. If I was to take 4 people and find their average of their IQs, I'm now trying to figure out where that average would fall. Okay? So if you think about it, the more people that I look at and take their IQs and average them, the closer that would technically have to be to the actual mean of the general population, right? So that's the whole point of averaging, correct? It's like it's pushing you towards the middle. So the more we look at in terms of that, the closer we're going to get to what should happen. All right, think about it like we were talking about in we were doing in chapter 4 and 5, where we're flipping a coin. Okay, you flip a coin once, you can get heads, right? And then you say, oh, I have a 100% chance of getting heads. Well, no, you flipped it once. If you flip it 10 times and you get 7 heads, well, it's like I get a 70% chance of getting heads. Okay, that's an experiment, right? If I flipped it 1,000 times and I got 510, now we're at 51%. We're getting closer and closer the more we do to that 50-50 that should happen. Okay. The 100 in this case is what should happen. That's the mean. That's the average IQ of the entire population is 100. That's what should happen. So the more that I take, the larger the sample size that I take, the closer or the higher the chances that I'm going to be closer to what should actually happen. Does that make sense? That's why your standard deviation is getting smaller. That's why it's getting closer and closer to it. I'm not saying when I took that sample size of 4 that every time I do a sample size of 4, I'm getting a mean of 100. Okay. I'm saying this is the mean of all the means. But we can't do that because that means we would have to do a sample size of 4 out of 7.8 billion people, which would never be able to happen. Okay. The math and everything else that they've done and the large studies and everything else that they've done, just like flipping a coin, the more and more that you do, it ends up coming back to that average. That's going to happen. So the chances that I get there, my percentage is getting closer. When I did a 16, it's getting even closer to that. All right. So 1, 2, 3, 4, 5, 6, 7, 8. Try that again. 6, 7, 8, 9, 11 people. So there's 11 of you in here. All right. So if we did 16 divided by the square root of 11, what do we get? That one's not going to be easy to do in your head because it doesn't work out nicely. But that's what calculators are for. 4.8. So we get 4.82. So if 100 is a standard deviation there, right? 95% would be 2 standard deviations, correct? Yes? Okay. So if I was to double that, and subtract it, there'd be a 95% chance that the average IQ in this room is between 90 and 109. Okay? What's wrong with the study that I just did? Nope. That wasn't a mistake. There was one error with my thinking, and I did it on purpose. What is everything that we talk about has to have? There's one key piece, whenever we're picking things. It has to be what? Starts with an R. Random. It's a random sample. When I did the 11 of you in here, was that a random sample? No. Okay. So remember that random is the key to everything. Okay. So while yes, there's 11 of you in this room, my guess would be that the IQ would be slightly higher than what they're talking about here, because you're not a random selection of people. You are people who chose to go to college and everything else. Now, if we're looking at 7.8 billion people in the world, if I was to randomly collect 11 people, all 11 people wouldn't be sitting in a stats class. Okay? So that's the key piece there. All right? It has to be random. But if I was to take a random sample of 11 people, there's a 95% chance that their average IQ of all those 11 people would be between 90.36 and 109.64. Okay. So because the more that I have, the closer and closer that range is going to be. Like we did 16, there's a 95% chance that it would be between 92 and 108. Okay, that's 95% chance that the average IQ between those people would be between that and that. That's what it's trying to say. So it's more than just looking at a single individual. We're looking at groups of people, basically. We're looking at groups of population. Does that make a little more sense on why it's starting to shrink? All right. There is what's known as the central limit theorem. So remember, let's see if you remember the number. I said that after we get past a certain number of samples or people or population or whatever we're looking at, that we would assume that it's normally distributed. Anybody remember what the number is? Anybody want to take a guess? What? If, huh? That's a little high. There is. I did say 1,000. There was a reason for 1,000. I'll tell you what the 1,000 was in a minute. Still high. 300's getting closer, but way high. It's 30. Yeah. All right. So once you get past 30, you can make the assumption that that data will be normally distributed. So once we take a sample size of 30 or more, we can assume that that's going to be normally distributed. If we have a population of at least 30 people, we can assume that the stuff that's in it is going to be normally distributed. Obviously, the more we have, the better that's going to appear at. But at 30, we can start assuming normal distribution. That's important because that allows everything else that we've been talking about to work. That's where the z-score comes in. That's where the bell curve comes in. That's where the average, the 68, 95, 99.7 comes into play. That's all in normally distributed. If we don't have a normal distribution, none of that stuff works. So what they actually showed was that anything over 30, all that stuff works. Okay. The 1,000 came in is that gives you a small enough percentage of change that you can reasonably understand that would represent the entire population. So we're within, if you ever look at a poll where it says plus or minus 3% or plus or minus 3.5%, that's looking at about 1,000 to 2,000 people. And they're making the estimations for the entire country at that point. All right. All right, let's look at some problems. So, birth weights. According to the document, birth weights of male babies have a standard deviation of 1.33 pounds. They want to determine the percentage of all samples of 400 male babies that have a mean birth weight within 0.125 pounds of the population's mean birth weight. All right. Do they tell you the mean birth weight? No. Okay. So we're going to start to look at why, in essence, it doesn't really matter, and how we can do all this stuff without actually even knowing what the mean birth weight is. What do they tell us? Okay, so we have our initial standard deviation. That is needed. when we get to chapter 9, we're going to look at how we could figure things out if we don't know that. But for the most part, if we're looking at a normal distribution, that is needed. So my standard deviation is 1.33 pounds. Okay, what else do they give us? The sample size. So my n in this case is what? 400. Okay. And they want to know with the what percentage is within 0.125 pounds of the population. If I don't know the population mean, we're looking for a percentage of change, right? So technically, I can set my population, my average or my mean to be anything I want. Because I just want to know the change between them. And what do we, when we're looking for change, we're going to subtract off the mean anyway, correct? So if you remember, your formula for z-score was the x value, or the x value, minus the mean, divided by standard deviation, correct? Okay. If this is just the mean minus x, minus the mean, these two values right there cancel each other out. So it ends up being just the x. So we don't actually have to worry about it when we're looking at percentages. We can just assume that this is my x divided by whatever my standard deviation is. Okay, that's my within. So in essence, what we're doing is we're making the mean 0. Because we're not looking for what the mean is, we're looking for how much it's varied. So we're looking at how far off it is. So if we make that 0, it doesn't make much difference. Okay? Yes.
It doesn't matter if it was like n minus x parentheses and then n again. It would be a negative.
It would be, except remember we're doing plus or minus it anyway.
Oh, yeah.
So it doesn't make much difference. But very good catch from the algebra. That was good. I was wondering if somebody's going to pick up on that. All right. So we need, before we start doing this, we don't have our standard deviation for our sample. What is my standard deviation for my sample? Standard deviation does not stay the same. What's the formula for it?
Divided by whatever that symbol is.
Square root
Square root, yeah.
400. So we got 1.33 divided by 20. So we got 0.0665. All right. So we want it to be within 0.125 pounds, right? So I need to find what my z-score is for that. So now remember my z-score was the 0.125 divided by the standard deviation. And if they were nice, this should be 2. Yeah, close. So 1.88. All right, so we go to our Z table. We're looking up, remember, we got to go both sides, right? So the negative 1.88 and the positive 1.88. So negative 1.88 is 0.0301. And then positive 1.88 is 0.9699. All right, so what are we doing with those two numbers? Remember, I'm looking for the middle, right? So what do I got to do? Subtract. So I got 93.98%. So if I was to take a sample of 400 male babies, a random sample, there's a basically 94% chance that they would be within 2 ounces of the actual mean weight of all babies. So if I told you the average weight of those babies were 8 pounds. Okay, so I took those 400 sample, my average weight was 8 pounds. I would be 94% sure that the actual weight of all male babies that were born was between 7 pounds, 14 ounces, and 8 pounds, 2 ounces. I wouldn't be 100% sure, be 94% sure. That it's somewhere between those. Now, I picked 8 pounds off the top of my head. I do not know the average weight of a baby. But that's the point of it. So even if I don't know the mean, we're starting to get to a point where if I take a random sample, we can get pretty close to what that actual value is going to be. Okay. All right. So let's do this one. So ethanol railroad tariffs, which I didn't know existed, but apparently they do. Apparently they charge. So does everybody know what a tariff is? So it's just a charge that they charge to do something. A lot of times it's when like imports and stuff like that are coming from overseas. If you ever order something from overseas, it's got to be, if it's under $800, they don't charge you a customs fee, which is basically a tariff. If it's over $800, they do. So, no buying your Louis Vuitton purses from France. Otherwise, you have to pay your tariff. All right. So the tariff in this case, they don't give us the mean, but they tell us the standard deviation is $1,150. If I randomly selected 500 shipments, what is the percentage that they would be within $100 of the actual tariff? All right, what's step one? What's the first thing I got to figure out? I need to find my standard deviation to the sample, right? Okay, so that would be done by doing what? By the square root of 500, which equals? Okay, so that's my new standard deviation. Okay. Now we're looking for the sample error, which is in essence another way to say what's the percentage of chance that I got it right or wrong. So what do I got to do next? I got to find my z-score, because the way that I could take my value and turn it into a percent is with the z-table. So I got to find my z-score. So my z-score, I'm going to do the 100 divided by the 5143. If I remember, was 1.97, 1.94. Okay. So now that I got my z-score, I got to go to my table, right? And look for the percentages. So what's the percentage on the low side? So 0.0262. And what's the percentage on the high side? Okay. So what do I got to do to those two? Subtract them, so that gives me a percentage of 94.79. Or no, 76. All right, so that's the percentage that's inside. So there's a 94.76% chance that it's within $100. They want the sampling error. So what do you think they're looking for? Right. And error is the opposite of it. So 5.24. So my error is a 5.24%. That's my error. So there's a 5.24% chance that I'm wrong and it's higher or lower. So it's, well, higher than 100 over or lower. Yeah, it's with outside of $100 outside off. Okay. Very similar to the baby problem, the weight problem. It's the same concepts, just different work. All right. Do this one. It's if you have actually your book, you can always flip in the back. It's seven. It's the problems actually from the second book.
Gosh, I take a picture of it
Oh,
and
so
then I
you,
put it on my iPad so that
That
I don't
works.
have to go back.
that works too.
That way I don't have to write out the whole problem.
Yes, that's always a good thing. I agree with that. I should just do it this way. we can start to see how these problems all are asking like the same process, but asking it in slightly different ways. And asking you to do slightly different things with the numbers. So they give us the mean in this case. They tell us the mean 72. And they give us the mean of the sample, the 78.3. So is that wrong? Didn't we say the mean has to be the same? Okay. So we assumed the mean would be the same of all the means, not an individual mean. Remember, that's the whole point. It's like the individual means might be different than when we're looking at that specific sample. That's what's giving us the range to begin with. So it's okay that the mean's different. That's possible. That's what we just looked at in the last two problems, actually. All right. So random sample of 29 casting workers. What assumption are we going to have to make before we actually do this? All this work that we're doing is based on the what? A normal bell curve, right? What do we say was the number that I could take and assume that it's always normally distributed? 30. This is 29. So we have to make the assumption to continue this problem that it is normally distributed, even though that it's not 30 people. Okay? So that's an assumption we're making. All right. So what's the standard deviation of my sample? What was it? So we did 11.2, and we have to divide that by what? Square root of 29, so you should get 2.08. All right, so my new standard deviation of my samples are 2.08. Okay. So what's the next thing we want to do? Okay, so to find z-score, we got to figure out what we're finding the z-score of, right? What are we finding the z-score of? What are we finding the z-score of? It's easier to look that way than this way. I got to turn my head crack. Okay. What are we finding the z-score of? So if you think about it, what are we trying? What is this study trying to do? We're now getting to the point where we actually are using the stuff that we've been talking about. It's not just theoretical in the situation. What are they trying to do in the study? What's the title of it? Worker fatigue. So they're trying to show that this group of workers is more fatigued than they should be. And they're using the heart rate to show fatigue. All right. If your resting heart rate is higher, that means your body's working more. Right? The higher your heart rate is, the more your body's working. So if you're a typical resting heart rate is pretty low, it's in the like 50s, 60s is a typical resting heart rate. So of the casting steel workers, the resting heart rate is normally 72 beats per minute. Okay, so that's a little high to begin with, but they're working in high temperatures and stuff like that. This group that they took is at a 78.3. Okay. So let's find out where that group rates compared to all the rest of them. Let's figure out the z-score for that. So So when we're looking for z-score, we're looking for the difference, right? We're looking for how far above the mean it is, correct? Or below, depending on which direction we're going. So we have to do the subtraction. So remember, the z-score is just your x minus the mean divided by the standard deviation. Same concept that we did before. So we're doing 78.3 minus 72 divided by that new z-score that I got, that 2.06. So what's the z-score we got? 2 point, what is it? 2.9?
I got 3.0. That's 1 point.
So we're doing 6.3 divided by 2.08, right? All right. 6.3 divided by 2.08. Yeah, it's 3.03. I totally screwed up my calculations, but that's okay because I know what I did wrong. So if we just did 6 divided by 2, you know you're going to get a number bigger than 3 in that case. So this has got to be a little bit bigger than 3. So 6.03. All right. So if we go to our Z table, we're looking up 3.03. We get 0.9988, right? So this group of casting workers has a heartbeat rate higher than 99% compared to all other resting rates. So if you were their union steward, because every factory, every steel plant is unionized anyway, if you were the union steward, what would you be complaining about? Overworked. The conditions are hazardous to their health. Okay. And you have the data to show it. Okay. That's how you can start to use the data to show things and to start making changes based on those things. And this type of data, okay, this type of data can actually sway decisions. Where if you just walked in and said, my workers were overworked, the boss is going to tell you, no, they're not, go back to work. But if you can walk in and show that their heart rate and their resting rates and everything else like that are higher, are well above what should be standardized. Remember, we said 3 standard deviations is starting to get, anything over 3 standard deviations is out of the norm. Like pretty much anything over 2 standard deviations, we can start thinking is strange. But anything over 3 is definitely out of the norm. So that's what this shows. Okay. All right. do A. What's the standard deviation of my sample? Yes. 2,276.32. And we want to know the error if we're assuming it's within $2,000 of the actual mean. So we would do 2,000 divided by that. So what's my z-score? What was it? 0.87. Okay, I got 0.88. That's fine. It was close. I was going to say it's depending on how you rounded at that point. All right. So then we go to the z-table. And I'm just going to share this. So we get 1894 and 81.06 is the two ends. So it's 62.12% between those. So my error is 37.88%. The chances of it being outside of that is 37.88%. So that's a pretty high error. All right. Do you have to assume that they're normally distributed to do A? Okay, but can we make that assumption? Why? Because it's over 30. We're looking at 500. What if the sample size was 20? No, we can't do that. Do you think life insurance policies would be normally distributed in general? If I was to go through and ask how many of you have life insurance, I'd be willing to bet the answer would be maybe 1, 2. Okay. So that's not necessarily a normally distributed thing. So we can't necessarily make that assumption. All right. So I couldn't do a sample size of 20. What if I did a sample size of 5,000? What would happen? I'm not going to have you do it, but what would happen? The standard deviation will get smaller. Let's see, what was it? I'll do it off the top. I'll do it real quickly. Now your standard deviation's down to 790. So now if you did 2,000 divided by that, now we're at a z-score of 2.78. Now my error would be a lot less, right? So that probably would be a good case in that situation. So this is where you figure out where that number lies. And that's where I was saying that 1,000 to 2,000 seems to be that sweet spot that most people go for. That gets us at about 3% variation. 2.77 is going to give us a pretty close. We're going to be really close in that, like within a couple percentage points for our error. Okay. All right. I would go through and start looking at the reviews at the end of chapter 6 and chapter 7. I'll have the review test up probably in a few hours. I have to go do it. It'll probably be the 7 questions again. Probably 3 from chapter 6 and 4 from chapter 7. Your chapter 7 problems are going to probably look pretty similar to what I was just going through and doing now, because these are ones from the end of chapter 7. So if the goal is to get you guys to start synthesizing it all, putting it all together, figuring out how to use it. Chapter 8 and chapter 9 become a little more of that. We get a little more involved in how it's actually used. So, all right. Any questions? Okay. I will see you on Tuesday.